This lecture is all about parity checkers and generators. And this is a really great topic because it combines a lot of your digital design knowledge into something that's really useful in many communication systems. Because parity generators and parity checkers allow you to check for errors in your data when you are sending data from one place to another place. So here we have a picture of a typical communication system where you have something that's generating data, say like a temperature sensor or something else that's producing data, and you need to send that data somewhere else. Whether you send it through a wire, through the air, through the water, etc. Lots of different types of transfer mediums, and then something on the other end needs to pick it up. So what a parity generator and parity checker do is they allow you to do a very simple error correction among the data that you send to the data that you receive. So let's see how this might work. So if you're sending 3 bits of data, here they're labeled A, B, and C. Say you want to send 101 on your line. And you are hoping that what you get on the other side is also 101. But what happens if you didn't receive 101? Maybe you received 001. Do you want to use that data? Or do you want to know that there was some error that occurred? Okay, so there are 2 different types of parity generations. There's something called odd parity, and guess what? There's also even parity. Okay, so for odd parity, you want to make sure there are an odd number of ones in the data that you're sending. And in even parity, you want an even number of ones. So in your parity generator, if you're trying to generate odd parity, you're going to take in your bits, in this case 101, and you're going to give 1 bit in addition to these bits to make sure you have an odd number of ones in the data that you send. So in this case, 101, we're going to have a parity bit become a 1 because then the data that we're sending, A, B, and C plus the parity bit, has an odd number of ones in it. It has 1, 2, 3 ones. Then when you do the parity check, if you have everything right, you'd have a 1011 come out, and your parity checker would say, oh look, I got an odd number of ones. I'm good. There was no error in this data. But let's say you had this error here. This B bit, or sorry, the A bit changed to a 0. Now when you check, look, there's an even number of ones. I know there was some kind of error. So let's do even parity. So with even parity, let's say this was the data we're sending again, the 101. Now we're going to send a parity bit of 0 because we want to say that we have an even number of ones in the data that we're sending. So again, if we get the right data, which in this case would be 1010, we'll check it and see, yes, there is an even number of ones in this. If we got the wrong data, in this case, let's say 0, 0, 1, 0. Now we see, oh, we were expecting an even number of ones and we got an odd number of ones, so there had to have been an error. So what are these parity generators and parity checkers made up of? Well, if you recall from your previous lesson, the XOR gate counts an odd number of ones. So XOR gives you an output of 1 if you have an odd number of ones. So we can use XOR gates to be our parity generators and parity checkers. So I'm going to pull up the textbook to just show you what that might look like. Alright, so here we have a parity generator that is generating even parity. So you can see here, if your inputs A, B, and C are all 0, your parity bit is going to be a 0 because you want to make sure there's an even number of ones in the input. Here we have 001, so our parity is going to be 1, so that way we have an even number of ones, or in this case 2 ones in the input. So here we've generated this parity bit, which if you stick this in the K-map, you see the familiar diagonal crossing, which just is the XOR gate, A exclusive OR, B exclusive OR, C. Similarly, there's your parity generator circuit. Similarly, you can extend this to the 4-variable K-map, which you'll see all these nice diagonals in the circuit, and again, that's just A exclusive OR, B exclusive OR, C exclusive OR, D. So these XOR gates are really great for these parity schemes. So if we go back to our circuit, just remember that a parity generator, if you want to send an odd parity packet, you add a bit to make sure you have an odd number of ones in your data plus the parity bit, and if you want to send even parity, you want to change the parity bit so that way you have an even number of ones. Alright. One last comment about parity generators and checkers is that they're only good at detecting errors if you have an odd number of errors. Only good at detecting an odd number of errors. So why is this the case? Well, let's say what you wanted to send was this 100, and you were sending odd parity. So that means your parity bit is going to be a 0 because you want an odd number of ones. Then what happened on this side, what you actually received was a 1110. So here you had 2 bits that were an error. But your parity checker says, oh look, I have an odd number of ones. I didn't receive an error. But you did, because 2 bits flipped. But you can't detect that. So once again, the parity is only good at detecting an odd number of errors. Now, you might think, well then what good is this as an error checking scheme? Well, the majority of errors in a communication system typically are only 1-bit errors. So by having this very simple scheme, you can do a decent amount of error checking by only adding 1 bit to the data you're sending, which is pretty good because if you wanted to do something more complicated, you might need to send extra bits for extra error checking, which adds a lot of overhead to the data you're sending. So even though parity can't cover all cases, it's pretty good at doing some sort of simple rudimentary error checking.